send just. Okay, so I think that we might start. So welcome everybody, and really thank you, Robert Griffin, for having accepted this invitation for giving a talk about all the work they're doing at IHMC, and potentially other, we will see. I mean, Robert Griffin, I don't know if you know him, but he's a research scientist at the Florida Institute for Human and Machine Cognition, also known as IHMC. So Robert has a great experience in humanoid robots, working along different topics, also with the experience of the DARPA Robotics Challenge. So really, it's for us, it's an incredible occasion to learn from someone who has been working on topics really close to ours, and about the challenges they've been facing and what is going on their labs. So Robert, thank you very much for this opportunity, and the floor is yours.
Thank you very much for the introduction. Just to verify, my screen's coming through okay? I've had some issues with that.
Yeah, that's okay. Yeah.
Awesome. So yeah, thank you for the introduction. As you said, I'm Robert Griffin. I'm a researcher with IHMC, and we're a not-for-profit research institute based out of Pensacola, Florida in the United States, where we mainly focus on, our group has been focusing on research on legged systems since the early 2000s, including things like humanoid robots, small running robots, exoskeletons, and even a handful of wheeled platforms, and also thinking about teaming. But today I'm going to be talking about really our efforts towards developing humanoid robots that could actually be potentially deployed to accomplish these kinds of challenging tasks. So I know a lot of you all also focus on legged systems, so this justification may not entirely be necessary. But when I think of humanoid robots, I think of what kind of tasks and operating places, or places do we want them to be operating in? And I think about, so this is me actually recording, going over some rocks and debris at the Camp Lejeune Marine Corps base in North Carolina. We were there for a project with the Army Research Lab a handful of years ago. And I really don't think that this is a task that could be accomplished by a ground robot that didn't have legs and hands. Other tasks you can also look at, we comically call this a traditional disaster area, which is actually Jerry Pratt's garage. So here, the user's having to climb over all kinds of different things. You have these small support areas that are incrementally spaced apart. Sometimes they'll need to be able to use his hands for balance. And there's just a lot of, and then retrieve objects. There's just a lot of these tasks that would be extraordinarily challenging, if not impossible, to accomplish with more traditional ground robotic systems. And really, that's kind of what we're thinking about. We're thinking about these kind of complex environments in an urban setting where robots have to be able to go through doors, climb stairs, ladders, be able to squeeze through these tight spaces like this crawl space in the bottom left, as well as go over rubble and overcome barriers. And that's kind of our whole thesis statement here, is that humanoid robots, they can do what people do. I can reach a high object, so can a robot. I can squeeze between these tight spaces. I can climb stairs. I can go over stepping stones and go over obstacles pretty easily. And if I were to compare this to other more traditional ground platforms and even quadrupeds, there's just the variability that a single platform can accomplish if you have two legs is a little bit less constrained. Tracked and wheeled bases, if I look back at these tasks, there's a lot of these that they couldn't accomplish, particularly given a finite size. Like if I want to be able to go over big obstacles, I need big wheels. If I want to be able to climb stairs, I need big wheels. But if I want to be able to squeeze under something that's low, I need a small platform. And then when you compare to quadrupeds, those are still going to be somewhat limited by their form factor, whereas a human, you have a very different profile if you turn sideways, and your feet, you only need really a place to step about every meter, and then you can go over pretty much any terrain. And to that end, we've been trying to design our own new humanoid robot. So the biggest reason for this is we really want to be able to operate at kind of a human tempo in relevant environments. For a long time, our research has been really constrained to a lab setting. I think that is the same for most of us. Although I know people like Claudio in the audience has actually taken his robots out into the real world, much more so than we have. But So we really want to be able to have robots that are faster, lighter, have this high range of motion, and an equal level of reliability. You know, we've been operating with our Atlas and Valkyrie robots since the DARPA Robotics Challenge. So, you know, going on nearly 10 years now, which is kind of incredible to think about. And we also want to just see, well, how flexible can we make a platform? How fast and strong can we make this system? So to that end, we've spent the last handful of years kind of designing Nadia. So we really started exploring designs in 2018 and starting putting together these prototypes. We use this kind of rapid iteration methodology where we wanted to test different joint mechanisms and things like that in plastic as opposed to metal, just so that we didn't have to commit to a design too quickly, because printing or cutting metal is both time consuming and expensive, whereas printing plastic can be done relatively quickly and relatively cheaply, which allows us to just iterate very fast and test out these different designs without having to commit to anything. So after about 16 versions in 2021, we decided to actually start manufacturing. We found something we were happy with. We started to manufacture the robot. We got it assembled around summertime and walking. And then in around March of this year, we finished building our upper body, which we attached to the robot here. So Nadia, as it is now, is kind of this mix between electric and hydraulic actuators. We have 6 degree of freedom legs, 5 of which are hydraulic, and then 1 of which is electric. Then we have a 3 degree of freedom spine, 2 are hydraulic, 1 is electric, and then 7 degree of freedom arms, which I'll kind of dive into the different design aspects of this robot here in a minute. Now, one of the big things that we did, apparently right now. So for hydraulics, this is the integrated smart actuator developed by Moog, also in collaboration with you all at IIT, specifically the HiQ group. And one of the reasons that we were really focusing on these hydraulics is just there's not an electric actuator that we have found that has the same power density as a hydraulic piston. It also is nice because you can, instead of having to put all this copper where you want the power, you can move high pressure fluid to where you need it. So you can kind of amortize and recenter where a lot of your mass is. So if you put your HPU of your robot into the chest, I then don't need all that weight in the legs. And once I have a good HPU, I don't have to, I've paid that cost already. I basically can use hydraulics throughout the rest of the robot. So as you can see here, we're really using the same piston or the same actuator throughout the robot, which has some costs that I'll go into later. But we chose that because if you look at these kind of curves, it's the only thing we were able to find that even comes close to hitting the actual power curves of a human being. The best electric that we were able to find is this blue line down at the bottom, which doesn't come close to the hydraulics. We also do this carbon fiber exostructure for the robot. The idea here is, you can have this large moment of inertia or modulus of elasticity or whatever, I can't exactly remember, but you put all the mass out of radially of the carbon fiber, so you get this really stiff link, in addition to that protects all of the internals, as well as potentially allows the robot to be able to make contact with most any part of the body, which is really this thing that humans are really capable at. We have this soft structure that allows those interactions to be done easily, but also, if I can lean against something without using my hands or feet. And that's a real direction that we think humanoid robots need to push in order to be able to operate in these kind of environments. We also designed these commercial off-the-shelf arms. So this was pretty much, we were running near the end of our project and we needed arms, and this was a quick solution. And it's worked pretty well. So we have these, we just used T-motors off the shelf and then carbon fiber tubes with a couple of metal cut linkages in there. And with that, we're able to get this long arm as well as a just massive workspace due to the range of motion of the joints themselves. We had looked at using these planetary gear box actuators that we developed for the pelvis, but just the size and expense of them and the time that it took to actually get the gears for it manufactured just was a little bit prohibitive in order to do that. So we've been using these arms on the robot since then. With that, we've been able to achieve some, we think, quite great performance when it comes to range of motion. You can see here the robot can lift its knee pretty high, and this isn't really exploring the full range of motion of the pelvis. So, when humans lift their feet, They're able to tilt their pelvis in order to get this really high range of motion out of it. We're not really doing that here, but we're still able to make really high step ups, as well as the robot can touch the ground pretty easily, and that's without using the spine or bending the pelvis as far forward, again, like a human would do. We can also do that kind of a lean, as you see here on the right, as well as get really wide stances and move the robot's center of mass around. Then when we do this kind of comparison to the Atlas robot that we have, you can just see, you know, the shoulder height is pretty comparable. The hip height is actually, I think that's not a perfectly scaled image on the top left, but the hip height is slightly higher, and that's because of the size of our hip mechanisms. But because of those hip mechanisms, we're able to get a much wider stance, as well as actually really do crossover steps. Atlas can just barely put its feet one in front of the other, but Nadia can completely cross over, and we think that that's going to open up a lot of possibilities when it comes to step adjustment. When you compare this height that the robot can actually step up, Nadia is able to step on top of these 4 cinder blocks without really having to cheat. Whereas Atlas here, the cinder blocks are not directly in front of it. It's having to heavily roll the foot outward in order to reach that same foothold. One of the next steps is to really kind of design our control architecture. So our control architecture that we picked for Atlas was really driven by some of the requirements of the platform and the DARPA Robotics Challenge, where we designed it in such a way that we wanted the robot to be able to hit these precise footholds in the world so that it can actually go over things like stepping stones, as you see here. In this case, the robot's given a set of footholds, and it kind of computes this dynamic trajectory that it can control about in order to reach the other side. And this enables a lot of tasks that the user can directly tell the robot, step here, 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 and it can navigate through these really complex environments. So this is kind of the architecture that we were centering around for Nadia. And this architecture is really based off of using kind of these reduced order template models. So in this case, we're looking at inverted pendulum dynamics, and specifically this concept of the capture point. And if you're not familiar, this basically is saying, okay, well, I think I can model motion of a biped as an inverted pendulum, where you basically have the base of the pendulum is the foot down here at the bottom, and then specifically the center of pressure within the foot. And then the end of the pendulum is the center of mass. And then we can assume that it's a point mass, or we can have a reaction mass here to actually generate angular momentum. It doesn't really matter in this case. But the big assumption is that you assume constant height. So the center of mass is moving in this plane here at some kind of fixed offset from the ground plane, where then the leg's able to extend and retract in length. And when you do this, you can then kind of define this, we call it the instantaneous capture point. It has a couple of other names in the literature, like the divergent component of motion, which has been, championed by both the Asimo team as well as the group out of DLR by Johannes Ingelsberger, as well as the extrapolated center of mass from the biomechanics literature. But at the end of the day, it's really just a point that from the dynamics that the center of mass is going to converge to. And using that, we can actually control this capture point by moving the base of our pendulum around, which is relatively intuitive. So if you think about like a cart pole model, if you've ever tried to balance like a broomstick, you can do that by moving your hand in the world. And so moving where that center of pressure is around, and you can then control the motion of the pendulum by shifting that weight. And so that's kind of the way that we define this controller. And in doing so, as you can see here, we're able to achieve on Nadia much faster locomotion than we were able to on Atlas. So this is us on our treadmill. And the big goal is, so we have an operator off screen just with the joystick controller. From that joystick controller, we're computing these desired footholds just in a thread and then sending them to our walking controller. And from that, the robot's able to, and it just assumes a constant velocity. So here the velocity heading is constantly changing. So the plane is constantly changing. But we're able to achieve really good, omnidirectional motion, whether it's backwards, forwards, side-to-side walking, all of that. And this has been really great that we're actually able to start having relatively good locomotion, not incredibly slow like Atlas. Sometimes you'll watch our Atlas and it's moving what appears to be quickly, and then you walk next to it and you realize it's depressingly slow. But that's not really the case with Nadia. So that's been pretty exciting to move into that direction. Kind of the next big thing is we want to build in this kind of dynamic stability to the robot. We don't just want it to be walking with just these fixed footholds, because that really limits the stability of the overall system. So to do that, we can actually go back to our inverted pendulum model, and we can look at the evolution of those dynamics over time. We can use that to kind of derive this concept of capture regions, which you see here. So you can see that, based on where I put my force, I have all these different force vectors going. The capture region is, if in one dimension, it's just this line. It's where I need to step in order to come to a stop, if it's the one-step capture region. And if you're using the full foot convex hull here, you can put your force in different locations. So you get this kind of set in the world where the robot actually needs to step to in order to come to a stop. So if I look at that here, you can then actually extend this to multiple steps. So my one step is this blue region. And then if I say, okay, well, I want to be able to take multiple steps to come to a stop, you then encode that by looking at how the dynamics would continue to evolve over time. And that tells you where you need to. And you can also observe here that eventually you kind of reach this limit. Once you start thinking about infinite steps, the additional area really starts diminishing heavily after 2, and it eventually drops off to a convergent series. One of the underlying assumptions of this, though, is that you can step anywhere within a circle. So you see I have this black circle kind of describing where the robot can step in the world, and that's not true. If this is my right foot, I can't step directly on the other side of my right foot, particularly with a robot like Atlas, but also a robot like Nadia. This means that, my reach in this expansion, this underlying equation is wrong. So I need to take this into account. And you can actually do that by looking at kind of your reachable set and expanding about that. And when you do, the robot, using this kind of capture region approach, you get a pretty robust response. We were pretty happy with this. Here's me pushing on it with a boxing glove attached to a PVC pipe, which is a finely tuned instrument that we developed here. One of the big challenges about this, though, is I'm having to be really careful when I push the robot. It's really sensitive to the actual timing of the disturbance, just based on a couple of things. Mainly the fact that if I add I have this really long transfer duration. So if I don't push the robot while it's right at the beginning of swing, I'm probably not going to be able to recover from it very well. And that's because even if I look at having a 0.5 second swing, if I then add this transfer phase in there, and even if it's just 0.2 seconds, the area of my capture region gets reduced dramatically. So that just shows you, that 0.2 of a second is extremely important. And that has to do with the exponential relationship between where the capture point is in time, coming from the inverted pendulum. So I can actually do this by looking at, okay, well, let's kind of treat my capture point location as a phase variable to some thought, and say, well, where through my dynamic plan am I? So if my capture point is at the very beginning of the plan for transfer back here, then I should just say, oh, my phase variable's at 0. If it's near the very end of the plan, my phase variable's at 1. Since somewhere in the middle, it's about 0.5. You can kind of see, if I were to do this projection, I can compute like an adjusted time remaining down here, where if my actual time remaining is 0.8 or 0.3, you can see as I move this thing or move my capture point around, you can see where it projects to along those dynamics, and you can see how it changes the amount of time remaining. And when I do this, you're able to get much more robust disturbances where I'm not having to be anywhere near as careful as to when I'm pushing the robot, because it's able to basically terminate transfer early and then take quick swings as necessary. So deviate, because I have prescribed some nominal timing for the robot, but it's able to deviate from that as it sees fit based on the capture point conditions, capture point state. And this has been really great. I'm able to push the robot relatively hard. It's not, incredibly hard, because it still doesn't have this knowledge of like anticipation. So it doesn't know that it's going to get pushed. This is purely reactive behavior. Whereas I think people are really good at, leaning into a push that they see coming. This doesn't have that capability. It's having to rely purely on reaction. One of the next things is, one of the disadvantages of just having the one size of ISA actuator that we have is that we have these really heavy legs on the robot. So, we have all this mass in the shins, which means that you have all this distal angular momentum. And it's completely oversized. We get about 900 Newton meters of torque at the ankles, which is incredible, but also completely unnecessary. But because of that, we can't just treat it purely as a point mass, because, you know, we're swinging these feet relatively quickly through the world. So to address this, we can use the kind of the 3 potato model, where you have the trunk, which is 1 potato, and then you have these 2 foot potatoes that have a small amount of mass in it. You can actually look, one of the problems with this is it's not incredibly accurate. So if you have kind of this plot that we have here, you can see that the blue lines are the actual angular momentum of the system, and the black lines are the estimated one from this 3 potato model. And so there's a lot of kind of nuance of the angular momentum that the 3 potato model misses. So to compensate for that, one of the things that we're looking at is to actually learn a residual model. So take this data, you know, we have a really accurate estimate of the angular momentum itself. We know the foothold, we know the leg trajectory. What would the resulting angular momentum actually be? And then you can learn that delta to make the 3 potato model predict correctly what the actual angular momentum of the system is going to be. In this case, you know, you still have the underlying parameterization of the 3 potatoes, so you're just learning that residual. I mean, we're pretty excited about getting this to work. On the robot, we've noticed a few issues that we're still trying to iron out, but I think that this is a good path forward for a lot of it, because it really does make the correction correct, whereas it was qualitatively close, but not quantitatively. Now it is both, you know, qualitative and quantitatively accurate. One of the other big things that we've been pushing into is thinking about multi-contact. So if you actually are, you know, we've been designing these kind of operator interfaces to allow a user to both specify contacts in the world that the robot has, as well as manipulate the body and through these different poses in that configuration. So here you can kind of see, if you place the right hand in contact, you have this region on the ground that's this region of static stability in the environment that you can move the center of mass to. Whereas if you were just your feet, obviously it's the convex hull of your footholds, where here you can see that it's significantly larger. And in doing this, we can actually load from hot file and then manipulate the robot, and you can see what it's capable of doing. This really opens up a lot of the advantages of a humanoid, and the fact that the robot can now lean much further forward to reach objects that would otherwise be completely inaccessible. So really improving that workspace. You know, the workspace in Nadia is great with the arm as it is, but you have this floating base, you should use it. One of the other big areas of work that we've been working on is actually adding in this kind of user-driven automation to the robotic system. This kind of comes out of our work in the DARPA Robotics Challenge. So in there, you could observe, you know, we came in second in that project, in that challenge, and we had an hour to accomplish relatively basic tasks. And you can see here kind of the breakdown of that hour, where the robot was only moving 35% of the time. The rest of the time was spent with the operator figuring out the exact commands to send it, trying to, you know, localize in the world where the robot is, get this kind of situational awareness in order to direct the platform correctly. So the idea is, if we could actually cut down that idle time, you can, the robot's continuously moving, you can now have a robot that can move 3 times as fast as it was able to move before. So to that end, we've been exploring this kind of semi-autonomous behavior framework. So here we have a mocked up task where it's kind of an exploration for bomb recovery. So you had a user drop a position to navigate to on the other side of the cinder block field. The robot then walks over, sees a door. The operator indicates, yes, open the door, then automatically does a parameterized door opening routine. Then it notices there's debris in the way. It's not really able to reason about how to clear that. This is complicated because the debris could be in any configuration. So we have a really nice virtual reality operator interface that allows the user to go in and move everything out of the way. You can then hit resume. The robot then goes over, notices the push door, executes the push door routine. Once it's to the other side, it actually sees these stairs, and the user says, yes, climb those stairs. For this one, the robot has to build up a model of the stairs ahead of time. It executes a handful of the steps, then proceeds to go through the next of the task. This is sped up at about 10 times actual speed. When it gets to the top, jumps back into VR, and the user is able to recover the bomb, then it goes back down and you dispose of the bomb. So to do this, we've been building up quite a few different tools in order to make this possible. One of the first ones that we looked at was, modeling the environment as these planar regions. This gives you a nice convex approximation of the environment in a way that's really both data efficient and also mathematically efficient, because you can use all these convex tools in order to do your planning. The problem with this approach is it takes a little while. We have this spinning Hakuyo single point scanning LiDAR that was kind of reminiscent, or kind of a relic of the Dark Robotics Challenge. And it takes about 20 seconds to build up a fairly accurate model of the environment. So to address that, we've kind of been exploring the use of depth cameras. In this case, it's a time-of-flight camera or solid-state LiDAR, where we then can punt the computation onto the GPU, and we're able to get computation times of about 250 times a second, so way faster than the sensor speed, which is fantastic. We're able to get these planar regions in real time, just in a relatively limited field of view. So to that end, we're also looking at, extending this to multi-line scanning LiDARs. So taking in these kind of unstructured point clouds and getting big planar regions out as obstacles and things to actually be able to localize against, which is something we're pretty excited about. This does represent a really efficient data structure, as well as a really informationally dense data structure. You have large flat regions with nice surface normals. If you feed that into this kind of a factor graph approach and you add in these planar region factors, you can come up with a really nice SLAM system. Next, we can actually feed these planar regions into just an A-star based graph search algorithm. So here, we are discretizing the world as like this 2.5D dimensionality graph. And then we can snap the footholds using just some really simple convex geometry. And we can then just have a user say, walk to this goal. In this case, I placed a goal on the other platform, and the robot was able to come up with a footstep plan to cross this balance beam. And then I also just placed a goal on the top platform. And we did this. This is actually during the open house where we did this run for about 30 minutes, just going up and down. From there, though, we really need to also be able to have this kind of long distance LiDAR. So to that end, we can build up these height maps using our ouster, just using a pretty basic height map algorithm. And you can then do an A-star search for path planning. One of the things that we did for this was we kind of did a two-phase approach for it, where you come up with your basic phase where you have this kind of traversability estimate of the environment. And then you can smooth the path in order to try and minimize that, or try and increase that traversability as you go along, as well as do things like pushing you away from the edges of the stairs. A lot of traditional approaches we noticed would kind of hug these edges, whereas, that's really not ideal for a humanoid. Repeat. Then you can kind of couple all of these different algorithms together where you have a height map, then a body path. And then in real time, you can be actually getting these rapid planar regions in and planning footholds in this kind of look and step behavior where the robot is just looking at the local environment and figuring out where it needs to step in order to reach a goal. And when you do this, here we've placed a goal on the other side of the room, and the robot's able to, as you can see, it can be, as it receives these new planar regions, it then requests a new footstep plan from the footstep planner at every step increment. And the robot's able to then relatively quickly, or as quickly as Atlas can, walk across this terrain. And we're pretty excited about this because this allows us to do a lot of fun things like react to these kind of dynamic environments. So you can see here, again, we've placed a goal. The robot's coming up with these plans. And I can shove things into the way. And because it's getting these environment models so quickly, the robot's able to replan and react to these environmental changes. For the door behavior, we've used a relatively structured architecture where we have a set of individual tasks that are kind of parameterized by the door. We are having to kind of cheat and use these QR codes. We're hoping to replace that with object recognition in the near future. But one of the things that we do here is we've tried to design the actual sequence of tasks in such a way to create really reliable execution. So you'll notice here in a second that once the robot actually opens the door, it then puts the other hand between the door frame and the door to prevent it from being able to shut it. And this is kind of in response to the arms on Atlas aren't exactly the most accurate. And then the spine also, you can kind of see even as it's opening, the robot's yawing a little bit about the spine. And that has caused it to shut the door by accident and in practice. So by putting the hand in the way, that doesn't happen. Then because it's so big and it's moving so slow, it has to kind of wrap the arms in front in order to make it through the door frame. From there, in order to accomplish that task that we showed earlier, you can kind of come up with an overarching behavior architecture that coordinates all of these different sub goals and sub behaviors, including some real-time interrupts like obstacle detection, goal placement, and object detection. I mean, we can just call this kind of our operator or our explore environment behavior. And we are really looking at trying to now use this concept of interdependence to figure out where are the cues that we need in order to increase reliability on these things moving forward. One of the other behaviors that we've developed just as kind of a exercise in algorithm integration and sensor fusion is this idea of person following. So in this case, we just have a neural network that segments the environment into different objects. We're really only interested in the mask that describes a person. So, you know, we've taken that one person and we said, follow this one. You can then actually project the point cloud into it. So you now have this semantically labeled point cloud. You can then, for every person, you can define a new track that gets, you know, tracked throughout the environment using a Kalman filter projection, so that even when the person goes out of frame of the robot's cameras, the robot is still able to know where that person is in the environment and follow them. And then you basically have this defining a standoff distance, which you can see as this kind of dot in the top right, so that the robot is, which is then being fed into our look and step algorithm. So the robot's actually actively following the person through the environment, including over this rough terrain. One of the things that we've noticed, though, if we were to just assign hypothetical reliability percentages to these different behaviors that are required to execute this explore environment algorithm, is when you start combining all of these, even if the individual tasks are pretty reliable for execution, like I have a 99% approach door execution behavior, you know, the minimum here is 80, I think. Yeah. The combined total reliability of the overall behavior for exploring the environment is really, really low unless you have some ability to recover. So 37% is unacceptable. 99% is really acceptable. How can we, you know, and this is just a law of statistics, how can we basically increase the reliability? And we think that the key here is to be able to have quick operator intervention. So have a robot detect failure and then a human jump in order to help. So in this case, the robot missed the handhold and it noticed, oh, I was going to push myself over. I need to pause what I'm doing and I need help. I don't know what to do. So it stops the behavior. John, our operator here, jumps into VR and is able to then quickly, you know, move the hands through the environment, open the door, and then he just, you know, clicks a button at the end of it, and the robot resumes the behavior. So you see there, it just moves the hands, and it continues on. And we found this to be just absolutely crucial in order to increase the reliability of the overall approach. And we're really excited to start tying this in with Nadia. You can see here, you know, this VR teleoperation allows you to do all kinds of things. You know, in this case, we're moving little bottles of super glue, which we think requires a pretty high degree of dexterity in reality. You know, humans can do it really easily because we can really easily figure out grasps. You understand what's what, like from an object perspective. You're able to really rely on your kind of cognitive capabilities that we just don't have yet in robots. But in the meantime, by giving these really intuitive interfaces, you're able to accomplish tasks that would otherwise be tremendously difficult and take a very, very long time. And then with Nadia being much faster, we're actually able to start operating, you know, at or near human speeds. You know, Atlas and Valkyrie, you have to move really slow in order for the robot to actually execute the tasks, to the point that it was kind of awkward and honestly kind of exhausting. Whereas, you know, here Sylvan is able to just move, you know, at a fairly deliberate speed, but not necessarily what I would call slow. The biggest slowdown is just verifying that he's going to grab the thing he wants to grab there at the end. So it's kind of coupling this perception into the teleoperation feedback loop. We're hoping to, in the near future, upgrade Nadia further. So doing things like putting all the HPU power on board. So right now we're operating with kind of this off-board pump. So we've been working on a test stand HPU so that we can actually, move this on board and not have these hydraulic tethers and take the robot out into the real world. We're also looking at these higher torque arms. So to do that, we've developed these really, really nice electric actuators that we're really excited about. We're starting to explore to install on the upper body. With that, we'll be able to, move things that are meaningfully heavy. Right now, we're limited to like balsa wood 2x4s and those plastic sticks that you saw. And also, we can do multi-contact. So we can actually lean and do some of the demos that we're trying to highlight. And then to also tackle the fact that, the ISAs are great. They've worked fantastically well. They're entirely too large for our shins. So we're actually doing these custom hydraulic pistons that we're wrapping up designs on now. And the idea here is to reduce that kind of distal mass and inertia of the legs and be able to really optimize where we place things in the world, in the robot, in order to achieve, nice form factors that are more inertia friendly. We've had quite a few different partners and performers on these projects. So we have a for-profit company that we've spun out called Boardwalk Robotics that's supporting the Nadia development, as well as some of the commercialization of technologies. IHMC is the main performer on a lot of the projects, but we also have a PhD program at the University of West Florida where different students have performed a number of the work that you've seen here. Most of the work's been supported by NASA, ONR, and Army Research Lab. And we've had some fantastic partners to help with some of the technology development, including Moog. Actually, you all at IIT, specifically Claudio Samini's group, and then motor technology from Halodi and hoses from FHS. We have an amazing group here, a great team, which we're expanding. So this is actually our picture from last year. We're bigger now, but we're adding more faces. We're hoping to, continue excellent development. We moved Nadia into our high bay here. So you see Atlas hanging in the background. Atlas is now hanging from a post, and we're excited about completely replacing it with Nadia. With that, I'd like to thank everybody for listening. And as a reminder, we are hiring. This is everything from junior controls engineers up to research scientists to help go after, these great projects and use this new technology that we've developed. That, I'd like to thank everybody for listening, and I'd love to answer any questions.
Okay, Robert, thank you very much for this very nice presentation. So I think we can open the question time. So anyone who wants to jump in, please do not hesitate to raise your hand virtually, and then we can coordinate the questions. Yes, Victor, please.
Hi, Robert.
Hey, Victor, how are you?
I'm doing well, thanks. It was great to see the robot. Really nice. After the meetings we had, seeing the robot moving like that is awesome. It's a little curiosity regarding the ISA that you are replacing for the sheen to reduce the inertia. You are still replacing by hydraulic with hydraulic actuators, right? So
Yes.
you are, but now resizing because of the torques that you need for the ankle. And that's why you are gaining in inertia.
Yeah, so we're trying to reduce the inertia because, one of the things we noticed was just with the hydraulics being both the physical size that the ISA is. So it's not, it's really compact for what it is. It's incredibly power dense, as you all know. I mean, it's a really great piece of technology, but it only comes in the one size, which is way, way bigger than we need for the ankles. So I know originally, and I feel like I'm preaching to the choir here, originally they were going to come out with two different sizes, and we were going to use the smaller size for the shin. But in this case, they didn't. So in that, we're pretty much just doing our own piston design. We're still going to use the same valve for the time being, but just doing a custom piston, putting the load cell in line with the pressure sensors and an encoder in there directly. And, we have it on a bench top right now, and it seems to be working fairly well, which is great. So that also has the advantage of, at least for humanoids, I know when you have everything located in one place, which is like the big benefit of the ISA, that comes at the cost of you now have a weird volume envelope. Whereas if I was able to locate the valve in a slightly different location, possibly even in the thigh, I then don't have to worry about having those valves in the shin, making as big of a volume envelope there. I can really do more on optimizing where exactly those different components in the frame are. You know, Boston Dynamics, looking at this, they did this whole integrated thigh design where they 3D print everything and machine everything directly into it. That's beyond our capability, funding levels, and frankly, interest. I mean, it would be really cool, but I think that, you know, it's very expensive. So I think that.
So you're saving in the size of the cylinder because you need a lower cylinder. You are also saving in the size of the manifold between the valve and the cylinder. This is how I understood. And then you're moving the inertia of those parts to the upper body.
Exactly. And then also we're saving on, we can, you know, more optimize the moment arm of the ankle. So, you know, here in the old design, you have a fixed actuator. So now your only real optimization variable there is going to be your moment arm at the ankle. If I can both pick my cylinder size from a flow rate, I can then also choose I have two control variables now. I can pick the cylinder size and I can pick the moment arm for at the ankle joint. So I can kind of really pick what's right for the that specific joint need.
Okay, cool.
Sorry, Robert, to interrupt. I really don't suggest to move the valve away from the cylinder, because then you're gonna have a dead volume that will slow down a lot of bandwidth of your actuator.
Yeah, I think that, you know, that's one of the things we're playing with a little bit, is how far you can move the valve before it really affects your control bandwidth because of that exact concern. I think like moving it to the upper thigh is a bad idea for sure, like you're saying, but moving it 6 inches away into the like lower thigh itself, we may be able to get away with that. I think that's kind of a variable that we're playing with.
Okay, cool. No, just to be aware of that. It's
thanks.
affect a lot.
Yeah.
That's great. Nice to see you, Michele. So, any other questions in the audience? I see Claudio showing up. Claudio, I don't know if you want to intervene. Or...
I will, but I think Aditya had a question first. I'll come soon.
Yeah. Aditya, yeah, please proceed. We do not hear you, Aditya, so probably you got an audio problem.
Maybe I can use this chance. Robert, it was great to see the results and updates on Nadia. We haven't caught up for a while, so this was excellent to see. I have a question regarding the HPU. You saw some prototype image. Can you tell a little bit more? I saw a Takako actual piston pump there. It's a high flow rate you plan to have.
Yeah. Let me see if I can go back here. Yeah. So right now, as you said, we're just using this Takako axial piston pump. I think we're kind of coupling that with a Haloti motor or frameless motor right now. We're not 100% set on the motor itself, but you know, we managed to pull the flow rate requirements and model the flow rate pretty accurately. And then we can run our simulations to figure out how fast we want to go so that we can calculate the flow needs of the different actuators. The one thing that doesn't take into account, I know, is the leakage, which is not great. And then I think that, you know, from our modeling, we're probably going to have to submerge the motor in order to have it operate at a high enough voltage in order to actually be able to run it quickly enough. But I think it should be good. Right now, we're still in kind of the preliminary design phases, just testing out driving the motor and the actual pump itself, but really pulling the Takako pump and redesigning it, like the housing and everything. So
we should catch up about HPU soon, because we're also developing our own submerged HPU. I think we can exchange some results.
For sure, that'd be great. Yeah. think I remember you saying that at ICRA, so that'll be exciting. I need to close the loop with the rest of the team.
That's great. I think that now Aditya, if you want to ask a question.
Yeah, actually, I hope I'm audible now.
Yes.
Yeah, a little bit of noise in the background, but it's okay.
All right. So, Robert, first of all, thanks for the talk, and it was super interesting. I had a question out of curiosity about the path planning that you do here. So I just wanted to ask, like, how do you place the points, and how often do you build a tree? Like, do you build a tree on a periodic interval, or is it event driven? And also, why specifically the A-star algorithm?
Yeah. So there's two different algorithms running right now. There's the height map that's being built from the Alster. Right now, that's not running in a real-time updating loop, so we kind of get an assumed goal that the robot plans towards from the beginning, and then you just hand the robot a path. One of the nice things about that is then a user can manually draw a path that you want the robot to take. But for the footholds themselves, we're basically rebuilding from scratch every step. So we're taking in these planar regions that are being calculated on the GPU in real time. Then we're doing an A-star search over those planar regions using a grid that's discretized, I think 2.5 centimeter discretization. And so it's in that case, I mean, it's a really basic A-star algorithm. I think that a lot of the quality comes from just making it focus on these planar regions and then a well-defined cost function for a humanoid robot, as well as thinking about the idea of, I don't have to get my foothold entirely on the stack. It allows you to do partial footholds, and then in a post-processing phase, you can actually optimize the location of those footholds where you move them a little bit further into the convex region using just a simple linearized QP.
Okay, so was the decision based on like just optimization of the resources?
I'm not sure if I understand what you asked there.
So I understand that you were using A-star, and yep, you also rebuilt the tree periodically. Was that a decision based on optimization of your hardware?
It was, so I think that it's this kind of graph search approach, while discretizing the environment into a graph isn't necessarily ideal, the ability to compute exactly where you want to step in the world kind of fits with the tasks that we're trying to accomplish, where the environment's complex, as well as the control system that we have, where it consumes these specific footholds in the environment. Whereas a lot of robots, you send a velocity and they track that velocity. You then don't necessarily have the same control over precise foot placement. And so given the controller and the desired objective of the controller, we wanted to be able to specify specific footholds. And if you're willing to accept that you can discretize and just kind of pick footholds in the world, then this kind of graph search works really well. I'm not convinced that A-star is actually better than a depth first search algorithm for this. I think a depth first would be completely fine for a lot of relatively simple footholds. But A-star has been really good when you start dealing with these more complex environments where height changes, because I think that there's a lot of hidden cul-de-sacs, if you're familiar with like the cul-de-sac problem. There's a lot of ones that would be hidden based on the definition of reachability that you have from like your stance to your upcoming foothold. And so by having it do that, as well as coupling it with this body path plan to help avoid these cul-de-sacs, where that's kind of also your part of your heuristic function, it's really been pretty great. And it is event driven, like you said, so replanning every step.
All right, I understand. Thank you so much.
No problem.
Okay, any other question from the audience? So there is a comment from Connor, who is one of our visiting students from Virginia Tech.
Yeah,
I just want to.
Connor visited here a few years ago, actually. I almost said a few weeks.
Okay. That's great. The word is small. So there is Stefano. Stefano, please.
Yeah, so thank you very much for the presentation. It was very very nice to see, and it was really nice to see the new robot. So I was also wondering how resilient it is to falls in case it falls down. I mean, given the design, it's a unfortunate destiny, the destiny part. So how can it resist to falls?
Yeah, so that's a really good question. Right now, it has infinite resistance to falls because we haven't let it fall. I think that, we're still pretty nervous about that. I think that the upper body won't be at all. It's not really designed to be very robust. We did a fair bit of destructive testing for the lower body where we actually, I think you might have been here for that.
I don't
where
remember
we
something.
we put one of the carbon fiber shims on the end of a like 10-meter long 2x4 and then lifted it to the second story of the lab and then had it slam down into pieces of concrete. And it was able to do that, 30-ish times before the carbon fiber started to delaminate. I think that everyone in the building was not very happy when we were doing those tests, but I think that kind of proved that this kind of carbon fiber construction works really well. As for the joints themselves, I mean, that's going to be a weak point, but I think that the bigger concern is we still have these big tubes or hoses and wires running on the outside of the robot in loops. That's kind of a big push on the next iteration of the hardware is to internalize all of that. I think that, we've been looking at how you can route them around the mechanisms. That was one of the big design choices that we made for the knee for choosing the mechanism that we did, because routing the hoses is really good to keep it internal. And by keeping all that internal, it'll then be protected. But that's really hard to do, especially if if you're coupling an electric pelvis with a hydraulic thigh, routing the hoses around the pelvis is going to be pretty challenging. But I think that, that's going to be a major focus of the next version. But I think that also there's something to be said for the fact that humans also aren't infinitely robust to falls. We're pretty good at falling. We have a lot of practice of it when we're really young. I have a 7-month-old at home right now, so watching her learn how to fall and everything has been really great. And so we get a lot of practice on how to fall and how to fall in a way in which we don't hurt ourselves when we're young. And I think that that's going to be key for these robots to be able to survive falls, because you're not going to be able to predict all of the ways in which they could fall and hit the ground and then design them in such a way to be robust to that. So you have to learn how to fall in such a way to protect yourself during that actual action too.
Okay, that makes sense. Thanks. Actually, while you were answering, I started thinking about the agility and mobility tasks. I mean, are you planning eventually to consider high degrees of dynamism, like jumping or running, or is it out of the focus for the moment?
No, I mean, that's on our roadmap. We haven't really done big pushes as of yet in it. It's been mainly just, we got the robot assembled in March. So I'm pretty happy with where we're at now. Now it's getting all the perception sensors on board, replacing all the things that we used to do with Atlas to do it with Nadia. But, pushing into this direction of really dynamic locomotion is something that we're very interested in. We just haven't really had dedicated effort or time to do it yet. But I think that that's something that we're going to start looking at, because we have a platform that, at least in theory, can do it. It would be nice to now start developing control systems that are capable of handling it as well. I mean, we've seen a lot of really amazing work in the field, at least in simulation, on these types of things. With newer quadrupeds, we're able to start looking at, okay, how well does this translate from sim to the real world for running and jumping and even just walking quickly. But humanoids, we haven't really been able to. There's only been Cassie was able to, but that doesn't have an upper body. You start to see Digit, the performance is slightly reduced. I think that it's not really going to be a running platform. So there's not really a whole lot of systems in the world that can actually do that proof of concepts on hardware. And so that's something that we're pretty excited about being able to explore.
Sounds great. Thanks.
Okay, so I think that we have time for a very last quick question, in case there is anyone. Okay, Silvio.
Hello, Robert. So thanks a lot for the presentation. During the presentation, you stated that one of the goals for Nadia is being even more reliable and maintainable, if I got it right, than Atlas. And I think one of the reasons why Atlas is known is that it's quite hard to break. And did you achieve this with Nadia, or you're still working on it? What's your feeling with the new platform? Is new, so it still breaks, or?
Well, it's new and it definitely still breaks, but we're working on it. I think that, is this like fine line of reliability versus capability. So I don't want to put words in the mouths of the Boston Dynamics scientists for the new Atlas, but I don't think that it is known as being quite as reliable as the one that we have. I mean, we've had this Atlas. It's not the same exact platform, but that thing's been running since 2014. The fact that it still is operational is a testament to the amazing engineering that went into that. But they also used a lot of off-the-shelf components to make it possible. So we haven't quite hit that level of reliability. I think that there's some reliability on our wiring that we're trying to fix still. We run into issues with the ISAs with contamination. The valves are really, really sensitive to that. We've also, had issues with some of our encoders. We had to add encoders in certain places after the fact, so the system wasn't really designed from the beginning to include them. And because of that, they're not as reliable. But other than that, it's been a surprisingly reliable platform for it being our first real cut at hardware like that in quite a few years. But I think the next couple months are going to be fairly telling as we start having it not be operated by the controls engineers, but be operated by the people that are focusing more on the autonomy, as well as just using it more on a day-to-day basis. So we'll see. I know originally we were trying to say, oh, yeah, you can replace any component on it in under 45 minutes. That was like the goal. We are absolutely not going to be able to do that. I can tell you that from right now. Just getting the valve or pulling the 3 piston unit out of the thigh takes 2 hours to do properly because it's just such a complicated thing. But I mean, it's still the goal. It's still the goal to be reliable and easily repairable.
Thanks a lot.
Okay, so that's, I think we're done. Robert, thank you. I also have a really quick question because probably I missed it during the presentation. What's the weight of Nadia? So. Right
now, I think it's sitting around, and you'll have to forgive me for this, I think it's sitting around 180 pounds. So okay. Probably something around like 85 kilograms, somewhere in there. And that doesn't include onboard computer. It doesn't include onboard pump. It doesn't include onboard battery. But, I mean, we are including a lot of stuff that's heavier than it needs to be. I think in the future, the weight of the individual components are going to come down, but we add in all these electronics and things. The goal is to have everything be around 200 pounds. 90 plus kilogram, more than 90, less than 100 kilograms. So,
and the height? The
height right now is about 1.8 meters. So I know that one in the right units.
Okay.
But it's the shoulder height is high. You'll also notice that it doesn't have a head. So
yeah.
But yeah.
Okay, that's great. That's a really nice proportion. Let's say, yeah, 180 for 90. That's cool. Okay, so Robert, thank you very much for this great presentation. It's been really a pleasure to see you again, and I wish you all the best for the great and nice developments you're doing there. And we hope to meet you soon somewhere at some conference. So thank you very much, Robert, and say bye to all the guys there.
Thank you, everyone. It's been fantastic.
Have
a good rest of your day. Bye.
Bye.
Bye. Bye, Robert. Thanks.
Bye, Robert. Bye.
Thanks. Bye-bye.
Bye.
Thank you. Bye-bye.
Bye bye.